Morning. So our last speaker of the meeting, Shinpei, will continue his talk on projective structures on surfaces.
Thank you, Pranab. Okay, thank you for sticking around to the last talk of the conference. And then, so we just continue yesterday's lecture. So our goal is to show this theorem. And then we have a CP1. We want to understand the holonomy representation of CP1 structures. And so this fundamental group of surface into PSL2C, we have this homomorphism, and then this homomorphism can be quite complicated. Like, it's not necessarily discrete, but then following two conditions necessary and sufficient conditions for this homomorphism to be the holonomy representation of some CP1 structures. And indeed, we saw one direction of the theorem, namely like those two conditions are necessary conditions. And then we, in this lecture, we show that those two conditions are sufficient conditions, meaning that given a homomorphism of this type, we can construct some CP1 structures on the surface with this holonomy representation. Okay? So let us recall, like, so that just recall the like is elementary if image of rho fixes a point in H3 union of CP1 preserves 2 points. In CP1. And then we also show the following proposition that if C is a CP1 structure on the closed surface of genus at least 2, then a rho lifts to phi1 of S, homomorphism from the surface group into SL2C, and then you see has now a CP1 structure on S with a single branch point of V2 then this representation does not lift. Okay. And another things we saw is that when we given a Schottky group, in PSL2C, we just need a rank 2. So it's free group, and as non-abstract group, it's just free group of rank 2. You can construct a CP1 structure on a surface. Genus to surface. So that those two elements go to different hyperbolic elements, and some other elements like this, so that they generate the fundamental group then they goes to identity elements under the holonomy representation. Okay, so by those arrows, I'm talking of the holonomy. Okay, and then from here we can cut into two pair pants and then we have CP1 structures on pair pants. And whose holonomy representation is isomorphism. From the fundamental group of pair pants onto the Schottky group. Okay? This is so those will be building blocks for the CP1 structures with the holonomy. Then I quickly sketch the proof for the sufficiency. So again, as I said, our goal is to given. So as I said, and then this is non-elementary, and we want to construct a CP1 structure on the closed surface. Okay. And then I quickly sketch the proof, the idea, but then let me do once again with more details, okay? So first step, we have this non-elementary representation. So we want to find multi-loop on S. Such that so we want to cut the surface into pair pants, maybe like this. Oh, okay. So these three loops is an example of a multi-loop on this closed surface, such that minus m is a union of pairs of pants. Let's say disjoint. And if you restrict the original given representation, which can be quite complicated, to the fundamental group of each pair of pants, is isomorphism onto a Schottky group. Okay. And then Schottky group, maybe I didn't say it clearly, but so it's for Schottky group, all elements are hyperbolic. Okay. Meaning that it has attracting and repelling dynamics with two fixed points, and in short, trace of this row of gamma is not, which can take any complex number, but it's not in the interval between -2 and 2. Okay, this is no identity element. So what this means, in particular, for this first step, step 1, we need to find a simple closed curve or maybe just let me call it loop. And then all loops are essential in this talk. Call it, say, gamma. What is gamma? Such that L, such that rho of L is hyperbolic. Okay? Because, I mean, in particular, those multi-loops, we are cutting original closed surface along must be hyperbolic elements. Because it's a boundary component of pair bonds. So this is for all pair bonds. So those, in particular, those loops must go to hyperbolic element, which is highly non-trivial because we just have like this representation. I mean, and we don't know the property of the representation other than the conditions are given. So later we see this. Second half of the talk, we'll see how to find a simple closed curve of this property. Okay, but let me finish the kind of outline of the entire proof. Okay, so step 1. So from here, so we have pair pants. So we found this nice multi-loop, and then we have 2 pair pants. And then and each pair of pants correspond to some Schottky groups. They call it gamma 1, gamma 2. So Schottky groups. By the condition for the multi-loop. And then from here, we can construct pair of CP1 structures. So for each pant pi, constructor the CP1 structure on pair of pants. By this construction. Okay. Before, so that how do you call CP1 structures? Call it CI maybe. PI. Pair of pants as before, so that I1 of holonomy of C1. So if let me set the developing map of Ci, Fi, and then holonomy representation rho I for this CP1 structure on the pair of bands. So that rho I is okay. So rho I is pi 1 of no. Rho I is the restriction of rho to this pair of bands, fundamental group of bands, okay, which is Schottky. Okay, so this is the second step. It's also like here, like we are calling a nice way that developing map is embedding. So originally, like we start with like 4 disjoint disks, CP1, and then before cutting the closed surface from the Schottky group, we have the fundamental group, a fundamental domain here for the action, and then after cutting a Schottky group, after cutting, so it's originally developing map is covering map onto the domain of discontinuity, which is a complement of CP1, a complement of the counter set in CP1. And then after cutting it, like fundamental domain becomes somewhere here, okay? For the pair of bands, so that you have kind of octagon, and then two pairs are two edges are glued, two pairs of edges are glued. Okay? If you move this fundamental domain by the Schottky group action, you see that the developing map is embedding. And then step 3, we kind of construct a CP1 structure on subsurfaces respecting the original holonomy. So we just need, but we want a CP1 structure on a closed surface, so we just need to glue them together nicely, okay? By inserting appropriate CP1 structure on cylinders between corresponding boundary components. So we have this C1, C2. Somehow, CP1 structure is up to the action PSL2C, but somehow we already fixed that. We take a nice representative of this representation in the conjugacy class, so we cannot kind of move around the pair bands. And then maybe probably like a boundary shape might be different. So for those reasons, we need to insert appropriate cylinders in between. So that we have such that we have the desired CP1 structures. So we know the step 2 quite well somehow. So let me go step 3 a little bit more detail. So how we found the cylinders? How we can glue pair of bonds nicely. So okay, so first, if you look at the pair of bonds, we already have pair of bonds. CP1 structure there, and then just looking at the neighborhood of this pair of bonds. So it's then the developing map. So CP1 structure here, zero part, this regular neighborhood is how can I say, is modeled on C star C goes to A Z. So it's modeled on the like exponential map. On the exponential map. Modeled as an exponential map. Yesterday we see it like a basic example of CP1 structure on tall line, and one of them is just make a Euclidean structure and then compose with exponential math. Okay. So boundary, if you normalize appropriately, like you take, so boundary loop is hyperbolic, so this loop is hyperbolic. So it has two fixed points, 0 and infinity, and then boundary. This boundary component loops kind of spiral toward 2. I mean, it can be look kind of straight, but in general, it kind of looks okay. Maybe just look for simplicity, just draw like kind of straight way, okay? And then like a fundamental domain developing map is given by exponential map. So here, can I draw this? There's no notation and. This regular neighborhood here, which is a cylinder, then you take a lift, you developing must look like this. I don't know which direction. More angle, so like this. And the holonomy representation takes this loop, boundary loop, to C goes to some dilation of this complex number. Okay. Just because holonomy is hyperbolic, and then developing map is embedding. So we have two of them. So we want to find cylinder here. So maybe color is not matching up, but so we want to find green cylinder, or maybe can one distinguish green and yellow? I sometimes cannot from the back. We have those two regular neighborhoods of corresponding boundary components. Okay. We want to find this blue cylinder. So we have So maybe you have similar picture. So we just need to, I'm drawing the same picture for one boundary component. We have another boundary component here. And then a cylinder appears here. The region in between. So this is picture in the domain of the exponential map, so it's in the complex plane, and this is P1. Okay. This is a regular neighborhood. And the transformation here is just translation, okay, by some complex number. So this blue, by quotienting out this action, I1 of a cylinder, which is an infinite cyclic group, we get a cylinder, okay? So this is a cylinder in the picture. The line does not, the line really looks like this. Or it looks like this, and then you have something like maybe like this in a little bit simple-minded picture, but and then we have like here. And the end point math, yeah. Infinity and 0, yeah. With the normalizations. So we took the fixed point to 0 and infinity. I mean, there's a couple of things you could ask, like why there's region in between here then? Because it's, I mean, this picture is 2 pi periodic, so you can just move like, you can exponential map with 2 pi I periodic, so you can just move, if there's overlap, you can move one high enough so that there's a region in between. Okay? That's one thing. And then another thing is that a priori, there's no region. Those curves, this is not the only curve which is invariant by dilation, okay? By this holonomy. Okay? So one boundary component might rotates much more than the other. Problem. Maybe one boundary component look like this, and then the other one might go something like this. Okay. Like accordingly, you can kind of twist. Like it might be twisted. Like I mean, there's no like a natural way of picking how much the boundary components are twisted. So there might be more twist. Depends on how you take the tail punch. Like how you cut the closed surface into 2 tail punches. Okay. So if it looks like this, then picture here doesn't look like this, and one boundary component might look like this, and the other boundary component look like this. So in C, so you can already find the blue region in between here. Okay. Like one more twisting correspond to like a going down by 2 pi I for unit lengths. Okay. But then this issue is coming from like how much the how much this kind of rotates. So when you recall, So when you take a Schottky group and reconstruct a CP1 structure on genus 2 surface, picture. So we cut into pair pants. Okay, we have this pair pants, but then there's a loop here that goes to identity element, okay, in PSL2C under the holonomy. We can twist, we can modify the boundary, this loop. Those two loops intersecting this orange loop by twisting, by then twisting along the orange loop without changing the holonomy of the Schottky group, the holonomy of the these pair pants. Just kind of holonomy-wise, you are adding identity thing, so it doesn't change anything. Anything means like it changes the CP1 structure, but it doesn't change the holonomy representation. This orange loop. By this way, you can kind of modify how much this boundary component are twisted when it is developed on the CP1. Okay? So that and using this carefully, we can resolve this problem. Okay. However, only issue is that, okay, for example, so simple question, where I did, so you could ask where I used non-elementary. I haven't used, I haven't used the lifting property yet. Okay. USL2C, and so here, point is that I think the point is when you twist it, you're actually twisting two boundary components. You're kind of changing the amount of rotation two when you do one then twist. So when you can do it here, you can make you can so here so at the last moment for the final cylinder, so you make cylinder here by adjusting the rotation number of one of them, and then you make a cylinder here by adjusting one of the thing, and then when you want to make the last cylinder to close up the entire surface, there might be trouble that, you're twisting two things at the same time, so it might not quite match up, okay? And then you need to use a, so step 3 actually tells that we can construct a CP1 structure on this closed surface, possibly with the branch point. Degree 2. Because by adding one single branch point, you can kind of adjust the rotation number, kind of a rotation number of this developing image. Okay, so you have this developing image, and then can I draw this? You can kind of add disk. You take another disk, and then you cut and paste on an arc. It's a little close to the bubbling construction which Stefano talked about. So maybe I can cut here, arc, and then you cut here. right? You cut and paste. Make it something like this. This. You have one branch point somewhere here. Okay? So you do this equivariantly. And then in this way, like, yeah, so if we can construct CP1 structure on S, possibly with a single branch point of degree 2, which corresponds to here. And then now, because we started with the representation with the lifting property, then it must be the CP1 structure without the branch point. And then whereas if we started with, you can do the same thing with start with homomorphism without the lifting property, and then in that case you get CP1 structure on a closed surface, but it cannot. We need to have a branch point on the surface because holonomy cannot reduce to SL2C. So in that case, you have resulting CP1 structure must have a single branch point. Yeah, but then you can modify too. I mean, so I think it's kind of like if you know, like you can. I think one increase by one and then one decrease by one. Something like this. So here, like last moment, you. Yeah, right. You can. The final part, you kind of tend to twisting along like here, like somehow this corresponding here, and then somehow one increase. Yeah. I think that's the intuition. Okay? Yeah. Mm-hmm. Right. Right. No. So step one, we already cut. I mean, cut the surface. Not only it's already shocky, but changing the pair pants. Oh, you mean the combinatorics? Actually, I didn't say clearly, but like, so the claim is that you can cut the pair pants. The multi-loop must have certain combinatorics like this. Some sort of tree. They actually cut combinatorics of multi-loop is somewhat specific, so it looks like kind of like tree. Like maybe. Am I answering your question or not really? Mm-hmm. Right. But need to be shocky, discrete, but like it's representation must be discrete if you restrict to pair pants. It's already shocky. Okay. From so your question how to go from finding a loop being hyperbolic to shocky groove. So actually need to find. So what they do is somehow. They do is actually need to find. They actually need to do a bit stronger than what I kind of said. Other just finding a loop called hyperbolic element, but need to find pair of loops. So step one. So sub-step one. Step one. Actually, need to find a pair of simple closed curves intersecting single point, say A and B. So they call it handle, but such that can I say A B. So rho of A, rho of B, hyperbolic. And then they generate A, rho B, generates a subgroup of PSL2C, which is non-elementary. So you need to find like two hyperbolic elements somehow pointing with a different direction. And from here, you can kind of you can make a lot of like a dent. I mean, hyperbolic elements, and then upgrade to a Schottky group. So you can. I mean, so like the point, like Vine hyperbolic, so means and the Schottky group, like you kind of need, as long as you have a kind of distinct directional axis, like you want to have a like long like a translation length to make it Schottky, right? So. Okay. Yeah. So you change it from there. Yeah. From here. Yeah. Right. So you need to take a. I think if I remember correct. Yeah. As you said, like you need to change from here, like not simple local. You need to kind of pair, and you kind of need to do something like A of B, and I think this generates Schottky group. A n, something like this. A power of B and B, and just make one translation like. Something like this, I think. Yeah, different simple local. So I don't. Okay, I mean, we can talk about later. Yeah. Oh. No, but you take A to the N to B, so you cannot get A. Something like this, along this line. So you take some sort of finite integral type kind of thing, yeah. It's something like this. Construction is subtle, but I think idea is something like taking like this. Once you have like hyperbolic element, you can generate like one hyperbolic element. You take like another loop which is non-trivial, and then you can do dent twist. You can make, if you dent twist along the hyperbolic element, you can make the translation like really large, so that hyperbolic plus like axis direction slightly different and long translation the length guarantees they are Schottky. That type of argument. Okay. Any other questions? Maybe more simple ones. Okay, so the last 30 minutes, I want to explain how to find like a single loop that goes hyperbolic element. How do I choose which region? Right. Right. So blue region is, you can see it in the region in between. Blue region is, so we don't see the blue region, so we have those yellow part, and then here you can see like this is a domain. So this is in picture in C. The domain of the exponential map. So we originally have two boundary components, corresponding boundary components. So corresponding to those yellow parts. I mean, And then you can move, because exponential domain of the exponential map is periodic under translating by 2 pi I n. You can just move then so that you can actually see that those boundary components. So you have two boundary components downstairs, and you see two lines here in the domain of the developing map, and you see you can guarantee that those two lines found some region in C. Yeah. So it's up to 2 pi grafting. 2 pi graph. So you can so it's okay. That's okay. That doesn't matter. Yeah. So I mean you can pick any one then. Right. 2 pi grafting doesn't change the holonomy representation. Right. Right. So actually, their theorem tells that actually like you have infinitely many different CP1 structures on this representation. So that Stefano's talk, people look at 2 pi grafting, but you can actually what Tenggren was saying, like you can shift like these things by 2 pi I, and you get like a kind of longer cylinder. Here, you can shift like a domain for one boundary component neighborhood to be higher place, and then you have extra like 2 pi and then so that you have somehow cylinder with like a this height 2 pi I. Which corresponds to like 2 pi grafting you saw in Stefano's talk. So 2 pi I is 0 mod 2 pi I, so that goes to 0 by exponential map. Okay. Any other questions? Last. Rho I1 of S PSL to C non-elementary then there is a loop S such that rho of L is hyperbolic. So we take some like generating this. A1 I phi 1 of S And then if one of them is hyperbolic, it's done. We just need to find one group that goes to hyperbolic. So the generating set consisting of separating those curves, simple loops, separating loops. We are done. So we can now assume all of those holonomies of the generating set, generating loops, are non-hyperbolic. So we can have like a elliptic, like a parabolic, or maybe identity, okay? But all of them cannot be identity because it's non-elementary. So we need to divide the cases. First, that we can find one of them is parabolic, and then we find a hyperbolic element somehow by combining. And then otherwise, and then we finish that case. And then last, we assume all of them are identity or elliptic elements, no parabolic, no hyperbolic. And then we find a hyperbolic element. Like a simple closed curve that goes to hyperbolic element. So like right now. Right. Oh, separating. No, non-separating, sorry. Non-separating one. Non-separating. Thank you. Yeah, non-separating one. Standard one. Okay. I'll say a little bit more. Yeah. So we have one. Non-separating. So we have one loop that goes to parabolic element. So suppose there is suppose we can find a non-separating loop. Such that rho of its holonomy is parabolic. Okay. And then I take generating set like this. Maybe. Take so that okay. I just switched the yellow one. This one goes to parabolic element. I take no. I think I. This loop. Goes around here, and then come twist around the one of the net one and coming back. This is a generating set for pi 1 of the surface. So all are non-separating. So just taking the, I find the generating set consisting of loops intersecting this parabolic loop one. each B1, A2, B2. And then claim. So then at least one of them is at least. Okay, let me just write for genus 2 case, at least one of B1, A2, B2 is non. Right. So maybe let alpha I be the holonomy of AI, and then beta I be holonomy of BI. Then at least one of alpha 2, alpha 1, beta 2 is not the identity, and does not fix the parabolic fixed point. No, alpha 1, okay? Because it's non-elementary. Otherwise, this holonomy fixes this parabolic fixed point, and that means that homomorphism is elementary representation. And then claim is that so in general alpha is parabolic, and then beta does not fix the parabolic fixed point. Then if you alpha to the n be better, it's hyperbolic. And this claim implies that in this setting that row of A1, and then one of this one, let me call it 1. And is hyperbolic. And then because those loops are intersecting yellow loop in a single point, corresponding to the twisting along. So this taking power corresponds to the twisting one of the red loops along yellow loop, and resulting loop is still simple. Okay, so we find hyperbolic element that goes to. No, we find a simple closed curve on the surface that goes to a hyperbolic element. And this is just calculating calculating a trace. So the proof for this, it's kind of fun. And then, yeah, many other parts of the proof uses calculating the trace to show a loop is hyperbolic. So it might be good. So you can put alpha by normalizing. You can put in this form 1101. So that alpha, if you take a power, it's 0 and 1. And then beta, so all of them in PSO2, right? Or ISL2. And then beta PQRS. But then, what is this? So here alpha fixes infinity, and then beta moves infinity, so this R here is not 0. So if you calculate a trace, wait. Trace of alpha to the n beta just simple n1 times PQRS, and just calculating only the diagonal entries, you see that P plus NR plus S is a trace of this composition. And when n is sufficiently large and trace gets big, and then it's hyperbolic element. Okay, this is not in minus 2 to 2. In large. That means it's a hyperbolic element. Okay, so now we are okay with parabolic one, and then we can assume all elements here are either identity or elliptic one. Okay. And then again, like we need to have at least 2 elliptic elements, as holonomy is non-elementary, and then axes cannot coincide. Okay, or axis must disjoint. We can. Okay, axes do not coincide, right? No. It's now non-separating loop one such that rho A is elliptic. And then all of them are we can assume AI and BI are in this picture all parabolic or identity. Okay. Oh, elliptic. Sorry. Thanks. kind of lemma. If we have a two elliptic elements, elliptic, and the axis, let me call it A of alpha and A of beta for axis. Maybe I should finish here. It's coplanar, meaning that the axes, which are geodesics in H3, are not contained in a single hyperbolic plane, total geodesic hyperbolic plane. So they are in the axes are somewhat in a general position. Okay. No, okay. No, thanks. No. In their composition, their product, alpha beta is hyperbolic. We have hyperbolic free space, and then we have two axes. Now, not contain a single hyperbolic plane. So the good thing about hyperbolic space, so I will prove it. A good thing about elliptic element in hyperbolic free space is that you can decompose into two involutions. Okay? We have like we have an axis, and then we have a rotations and some angles theta, and then you can decompose into you can take you can take this axis, and then you take some like orthogonal complement here. You have a plane. And you take the so two hyperbolic planes passing through the axis. Maybe I shouldn't draw this picture. Too complicated. So, so just look at the two-dimensional version. I just look at the plane. This is orthogonal to axis, and then this is orthogonal to the axis, and then you take. So you have a fixed point here of the rotation, and you have like a rotation angle here. You can subdivide this angle by half, and you take two lines here. And then reflection of those two, reflection of hyperbolic free space along those lines, their composition gives the rotation by this angle. Okay. When I say reflection along the geodesic, I'm actually taking hyperbolic plane orthogonal to this H2 containing this line, and then I'm reflecting the entire hyperbolic space along the hyperplane. So if you take two alpha and beta, rotations. Maybe take pi rotation. Okay, instead of like reflection, this pi rotation. It's the same thing. I mean, for this decomposition. Pi rotation. Then we have an axis of alpha, and then we have axis of beta. And then we take a geodesic, because they're coplanar. Now we can take a, as they don't meet at a point in infinity, we can take a geodesic orthogonal to both. We call L. So that, and then we have the rotation that R will be the pi rotation about L. And then R alpha pi rotation about axis of alpha, and then so no, we can take this. We take here for alpha, we take, so this is orthogonal. So we can take the hyperbolic plane orthogonal to this axis through the intersection point of axis of alpha and this geodesic orthogonal to both axes. Okay. Then take a another line in this orange plane, so that this angle is half of the rotation angle of alpha. Okay. And then take the vertical plane. No. Vertical plane. Yeah. Just pi rotation along this axis. Okay. So you can decompose alpha. So you have this orange red line, which has angle with L. The angle given by this white line, red line is half the rotation angle. So and then this is the alpha is given by rotation from this one, pi rotation along. Can I call this L sub alpha? And then in the pi rotation about L. On the similar things, you did beta equals alpha, and then R. And then R rotation about beta. You do similar things. The same thing for beta, and then you can that alpha beta is composition of pi rotations. Here, right? And because there's general positions, those axes, we started with a general position, we can see that it is have alpha and alpha beta disjoint, and then that means that when you have two disjoint geodesic and you compose with the pi rotations along those geodesic, we get hyperbolic element. So the translation length is twice as much as the distance between those two geodesic. Then I So the time is up or okay. So so I haven't. So somehow we finished the case that we can only find elliptic element, and within there, like we saw kind of generic case in the sense that the axes are generic, and then so I need to finish, but then so you need to do more carefully like about the other cases. So here, like so the generic here, like we assume that all axes are not coplanar. So like it's contained in some hyperbolic plane, or like maybe it's orthogonal to one of those, and then just need to carefully find the hyperbolic element, but we can talk if somebody wants to know more. Okay, and I finish here.
Any questions? No? Okay, let's thank the speaker again for the nice talk. Okay.
Yeah, let's thank the organizers for wonderful workshop, a wonderful place, like Subhojoy, Pranab, and Mahan, and Labourie, and Krishnendu, and yeah.